My name is Blanka Marková, and I am a public relations manager of this university, and I will guide you through this lecture. I hope you enjoy visit of Professor Friedman at our university, and you will attend another of his lectures held here during these 2 days. For this lecture, Professor Friedman will tell us about some life-changing events that lead him to the work that earned him later a Nobel Prize. I hope that you will find this presentation inspirational, and after the speech of the professor, you will have the possibility to ask him some questions. So, Professor Jerome Friedman is an institute professor and professor of physics emeritus at the Massachusetts Institute of Technology in the United States. Surprisingly, first he was interested in arts, and he got also the offer for a scholarship to the Art Institute of Chicago Museum School. But, as I know already, although he loved art, after reading Albert Einstein Relativity, he decided to refuse the scholarship and study physics at the University of Chicago, where he received his PhD later. Professor Friedman carried out his doctoral research under the supervision of Nobel Prize winner Enrico Fermi, an Italian physicist who is credited with the creation of the first nuclear reactor. Professor Friedman conducted research studies of particle structure and interactions with high-energy electrons, neutrinos, and hadrons. And now the most difficult part for me, because of his work on the innermost structure of matter in 1990 already, Professor Friedman received the Nobel Prize in Physics for, and I hope you will understand, pioneering investigations concerning deep inelastic scattering of electrons on protons and bound neutrons, which have been of essential importance for the development of the quark model in particle physics. Well, after all, Professor Friedman is a member of National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. And now it's my great pleasure to welcome Professor Jerome Friedman, and I would like to ask him about some words about his career path, about his life, and I hope that we all will enjoy it. Thank you, and I give you the word, Mr.
Okay, well, thank you for your introduction. I probably will repeat some of the things that you've already said, but perhaps in somewhat more detail. First of all, I was born in Chicago, Illinois, United States, in 1930. My parents came from Russia around 1912, 1913, and they settled in Chicago. And I was raised in a very difficult time. It was the Great Depression, and it was probably the worst depression to ever hit the planet since that time. And we had a very difficult financial situation. We had difficulty, paying the rent and having enough money for food. And these were difficult times. And as a child, I used to like to draw and paint a little. And when I went to high school, I decided to go to a high school which had a special art program, which actually I could draw and paint for 3 hours a day. And I took the minimal number of courses in mathematics, and I had one course in physics that was so bad that the only thing I could remember was that the teacher burned his sleeve in a Bunsen burner. It was such a bad course. For example, I never took trigonometry. And when I ended up going to the university, when I first got there, I didn't know what a sine or a cosine was. So you can imagine that this was sort of a strange decision. And let me say a few words about the decision, because there's more to it. First of all, Einstein was a folk hero in those days. He was a man who not only did great science, he was a humanitarian, he was for peace, and everybody basically had pictures or sayings of Einstein somewhere in their apartments or houses. And my parents really admired him tremendously. And I had heard about the strange things that he predicted, that, a moving clock will slow down, and a meter stick that moves very fast. I mean, these things have to move very fast, close to the speed of light. A moving stick will shrink, and that if you try to measure it, it appears to be a lot shorter. And these seem very strange to me. So I remember, I think it was the end of my third year of high school, I was walking through the Museum of Science and Industry, a beautiful museum in Chicago, and I saw this little book by Einstein. I picked it up, and the idea was that if you go through this book and you look at it carefully, you will understand special relativity, at least. There was a little bit about general relativity, but that wasn't the issue. So I said, oh my goodness, that's a great opportunity. So I got the book, and I spent the whole summer. I did have algebra, so I worked through all the transformations, the so-called Lorentz transformations, but which actually indicated how, yardsticks shrink and clocks slow down. And at the end of the summer, I said, this is really great, but I still don't understand it. And of course, there was a really very important principle there that, in a certain sense, I could not understand, because it's a very deep principle, and that is the principle of the invariance of light in any inertial system. And for example, if you have if you're on a train and you shoot a gun and you shoot in the direction the train is going, the bullet, basically, if you're standing on the platform, you see the bullet going faster than it would come from the gun ordinarily. You see the train velocity added to it. That's called a Galilean transformation. But that's not true with light. If I turn a flashlight on in a moving train, and you basically measure the velocity of light from the platform, it's still the velocity of light. It doesn't change. And that I couldn't understand. Of course, I couldn't understand that until I got deeply into physics and ultimately taught the subject at MIT for a number of years. But nonetheless, I was so interested in that, I decided, that's something I really, even though I don't understand it, I would like to understand it. I would like to understand things like it. So that's when I decided to go to the University of Chicago. And my art teacher was so angry at me, because he had written a letter of recommendation for me to get a scholarship at this museum school, and I was turning it down. And I felt terrible, but I felt I had to do what I had to do. And so actually, it turned out that I was I got good grades in all the courses I took. I didn't take the most challenging courses, but I got good grades in all my courses. And as a result of that, I was able to get a full scholarship to the University of Chicago, which I maintained. And in fact, the very interesting thing is that in all my education, going from basically beginning college to my PhD, I never paid 1 penny for tuition. Because after I finished the college, and of course the college there was quite an unusual college. It was a very experimental college. The idea was you'd come in and take placement examinations, and depending upon what your performance was, you could either get a bachelor's degree immediately without taking any courses, or you could spend 4 years. Well, I was in the middle. I had to spend 2 years, and it was a so-called great books course. There were no textbooks. All you did was you read great books and great literature and discuss great history books, great this and that. I mean, only the originals, and you discussed it. And I thought this was one of the best educations I could ever get, and I enjoyed it tremendously. But then, of course, when it was all over, I had to enter the graduate school in physics. And here I had no physics. I didn't even know anything about physics. Now, what happened at Chicago in those days, it was Enrico Fermi was the person who basically more or less gave the whole sense of how it should be organized. And his point of view was you let everybody in and you have a very stringent set of courses in which you fail people out. So basically, it was either sink or swim, and if you failed out, you failed out. And I was getting myself into it, and it was very difficult. I can't say it was easy. I had to learn mathematics and physics at the same time. I went into the first course was something called Physics 105, 6, and 7. And in it, they covered in 1 year what MIT at that time was covering in 2 years in physics, for the introductory physics. And every week there was a very difficult exam. The average was about 30 or 40 out of 100. And you know, many of us got really poor grades on weekly exams. And most of my classmates had really a good education in physics. Some had master's degrees from other universities, but they entered at that level because they wanted to work in a place where Enrico Fermi worked, and Enrico Fermi had attracted some of the best physicists in the world to teach there. And so I was saved by, in a certain sense, my own ignorance in the following sense. Many of my classmates who had more education, if they got bad grades in an exam, they got so discouraged they dropped out. I always said to myself, I love this subject. They will have to fail me out. I will not drop out. And I stayed with it, and I slowly caught up, and I was able to finish. And roughly 35 people out of 125 who finished that course. And it was because I decided I will not drop out. I would just stay till the end. And then I slowly caught up, and I took all the examinations you had to take. And when I passed my PhD exam, which qualifies you to do research, you know, I wasn't one of the best students in the class. I was probably somewhere in the middle. I'd been catching up continuously. And I decided maybe I'm not the best student in the class, but I want to work for the best professor. So I go up to Enrico Fermi, and I said, Professor Fermi, can I work with you? And I thought he would say, well, how did you do in that exam, or what is your class average in terms of grades? Didn't say a word like that. He looked at me, said, that's very nice. Come and see me on Monday. And I was just so overjoyed. It was like I had won the lottery. And I couldn't believe it. It was, you know, to be able to work for Enrico Fermi. And he was a wonderful man. He was brilliant, absolutely brilliant. You know, I know all the great physicists that exist, who are practically, perhaps not all of them, but a good number of them. And Fermi was just something very special. And he understood things at a very, very deep level. You could give him a very complicated problem, and he would find a way in 2 lines to get an answer to within 15%. This is the sort of man he was. He even did this once with the so-called Lamb shift, which is a complicated electrodynamic calculation. He got the answer in about 2 lines to 15%. He was phenomenal, a very kind man, a very nice man. So he gave me a thesis to do, and I started carrying it out. Unfortunately, he died while I hadn't completed my thesis, and I was in big trouble because you have to have somebody sign your thesis at the university to get your PhD. I went to a number of other professors to say, can I work with you? And they said, of course, you can work with, you're very welcome, but you're gonna have to start another problem. This is not a problem I want to do. And so I was really at sea. I thought I was really in deep trouble. There was one very kind fellow at the university named John Marshall. And he said to me, Jerry, finish your thesis, do a good job, and I'll sign it. And that's what happened. I finished my thesis, he signed it, and then of course I had another worry, because at the University of Chicago in those days, you had to publish your thesis to get a PhD. If your thesis wasn't accepted for publication, you would never get your degree. And of course my sponsor was gone, and it was a very sad time for everybody. And John Marshall wasn't going to, you know, he wasn't the sort to basically push my thesis in any way for publication. But fortunately, it was finally published. I got it published, and I got my PhD. And then, then I was able to continue on at the university for a year, because what happened was that Enrico Fermi had a so-called nuclear emulsion lab, and when he died, somebody had to take it over, and a young, very brilliant young physicist who had just become a professor took it over. His name was Valentine Talegli, a great character, and he took it over. And then something happened which was quite unusual. There was some very interesting development in particle physics. It was called the decay of the theta tau particle. And what seemed to be the case was that they thought this particular particle decayed into two modes, each of which had a different parity. Now, parity is a quantum mechanical concept that's, so they thought there was two particles, and actually there was a young Chinese duo, namely Li and Yang, T.D. Li and C.N. Yang, who were brilliant young theorists who had worked with Fermi. And they had proposed, oh, this was the same particle. But in this particular decay, there was something called the violation of parity. Now, what is parity? If you have the violation of parity, it means that if you change the sign of your coordinate system, the physical law changes somewhat. Now, isn't that a strange idea? That somehow, if x goes to minus x, y goes to minus y, z goes to minus z, it's not the same physics. And everybody said, well, that can't be. And so Val Talegli said, look, at these two young Chinese physicists have proposed a theory. Why don't we check it? So I said, look, and he asked a number of people to participate, and everybody said, that's a waste of time. Nothing will ever come of it. And I had enough sense to say, look, this is a very important issue. It's worth at least 6 or 8 months of my life to get involved. So basically, I carried out the experiment, and it turned out that these two young scientists were correct, that parity was violated in the so-called weak interactions. And this was one of the first 3 experiments done in the subject. We were not the first. It turns out I could have been the first had the following not happened. It turned out that Talegli had to go to Europe because his father had died. And I was getting the results from this experiment. You had to scan nuclear emulsions to get the results. And it's a laborious, tedious thing. Now, Talegli had left another person who was more senior to me as head of the lab at that point. And I started getting a positive result. I said, I need more scanning power. And this fellow said, oh, that's ridiculous. That's just a fluctuation. I want these scanners to be used for something more productive. So I didn't get the scanners I needed. So when Talegli got back from Europe, I got the scanners. We started getting the results, and we finally were able to publish it. But we were actually not the first. But it was significant enough that we got quite a bit of attention when it happened. And as a result of that, I was able to get a reasonable job at Stanford, doing something totally different, electron scattering, with another Nobel laureate by the name of Robert Hofstadter. And so I worked with him for 3 years, and I learned electron scattering. And then I got a job at MIT. And then what happened was they built an accelerator at MIT and Harvard. It was called the CA, the Cambridge Electron Accelerator, which I used for a few years. But it turned out that it was not a productive operation there. So my colleague Henry Kendall and I, when we found out that SLAC was being constructed with this new accelerator, a much more energetic accelerator, we said, gee, we'd love to work there. But how do you do that when you teach 3,000 miles away? So Henry and I went to see the head of our department. It was a very nice fellow by the name of Bill Buckner. And we thought that, well, we'll mention it, but this is going to be impossible. So we mentioned it, and Bill Buckner, who was a very, very fine fellow, he said, hey, that's not a problem. We said, what? He said, Henry and Jerry, what'll be, you'll be one professor, but you'll each get a salary. So what that really meant was that he and I would teach the same course, and I'd be in California for 2 weeks setting up things. He'd be teaching, then I'd come back, and I would teach for 2 weeks, and he'd be in California. And we set up one of the first distant research groups actually in particle physics, because we set up a group 3,000 miles away, and we slowly built it up, getting young people there, graduate students, postdocs. And then we decided to do electron scattering. And as I said, probably, and I don't know if I said this in the talk, but we started doing elastic scattering. It didn't produce anything because, as I guess most of you were probably at the talk, it takes a time average of the process, and you can't see constituents in the proton. And when we did the inelastic, we basically almost weren't able to do it. We had to promise to do something else and do the inelastic as a background measurement. And so the thing we promised to do was so dull and boring, we never published it. And we kept on measuring the background, and the background became so interesting that at some point, everybody was aware that this was some new physics. And then we continued the experiment, and that's what actually led to the discovery of quarks. But as I said in the talk, in both cases, namely in the parity one and in this case, I was warned by senior physicists, people who really were quite senior. For example, in the parity case, when I decided to help Tadlady do this experiment, in fact, I carried it out because he didn't work in nuclear motions. I gave a seminar at the University of Chicago, and there was a grand old physicist working there by the name of Gregor Wenzel. He was one of the great physicists from the time that quantum mechanics was being developed in Germany. He came up to me and he was smoking a cigar, and he said, hey, Jerry, that was a nice talk, but you know you'll never find anything. And so that was that. And then, as I said in my talk today, we had a terrible time with the program committee, and people told me that I would never succeed with anything. And in fact, what I didn't realize is I was up for tenure a short time after that, and I was told I probably wouldn't get tenure for working on such a project. But it ended up I got tenure, so it all worked out well. But this told me something. And what it taught me was that you have to think about what you think is sensible and right, and not be dissuaded by people who are naysayers all the time. You know, the safe thing would be to take advice of elders who said, this is not worth trying. But I had enough sense not to do that, and it served me very well in my career. So I say to young people, you know, don't do something that's foolish in the sense that it violates something that's been measured 10 times and you know that there's not a chance of it working. But if something hasn't really been studied enough and it's not understood, and yet people are dubious of your approach, try it. You may succeed. And if you succeed, you'll probably find something very, very interesting. So that's the end of my little presentation. Any questions?
Thank you very much. And I would like to ask the audience if there are some questions. Yes? I ask you to speak loudly to make microphone because of camera.
Sure.
Speak loudly,
Thank you for your wonderful talk, and thank you for your time today. I was wondering, I read about your signing the Humanis Manifesto in 2003, and I was wondering if you could talk a little bit about what it meant to you, what it really was, and what made you sign it.
Well, I think that human values are very important, and I think that when I read all the various aspects of it, I felt I had to sign it because I thought it was, you know, the fact that basically human beings have to abide by certain principles and values, to me, is very, very important. If we could do more of that, we would have less conflict, and the world would be in much better shape. So I thought that was very, very important. And you know, there are very few people even know that I signed it. I mean, you know, I've been asked, were there any negative repercussions? No, I don't think people paid much attention to it. But I think it's very, very important. I mean, there is so much conflict, and the truth of the matter is that we now have been able to, we've learned so much about nature that a real war is inconceivable. I mean, you know, look, there's fighting going all over the world right now, so you might say, well, what are you talking about? You can't always deal with people who are militants of various kinds. Those types of things will always probably go on. However, when organized nations go to war with the resources they have today, it's inconceivable. I mean, you know, you could destroy the entire civilization with atomic weapons or with biological weapons. I mean, it's possible. We have the knowledge to do it. So therefore, we can't let this ever happen again. And we try, and of course, these other things, these sort of militant wars that we have all over the world, you know, there are underlying causes which we have to work on there too, try to understand why they're occurring and what can be done to keep young people from getting involved. Very often young people get involved because they are impoverished, they don't have anything else to do, they're bitter at society, and they'll go after one particular issue after another. Like, for example, many young people are joining ISIS today. And why are they joining ISIS? It's not because they have been necessarily religiously inclined in any direction. They're dissatisfied with the world. And we have to do more to get enough balance in the world so there are fewer young people who would be attracted to such ventures.
Any other questions from the audience? Okay, maybe then I will try to ask, do you think that education might be solution for all these problems like IS and immigration and stuff like that? Because for me it's interesting that you said that your parents came from Russia, and I think that it must be really hard, you know, for them to give you some support to get the education, everything, but you were quite successful. You said you get the scholarship and so.
Yeah, well, look at my parents realized they had no formal education in Russia. My father learned English very well and became a great reader. Our home was just filled with books, and both my parents said, "Look, we're not doing well economically. The only way to make it in the United States is to get a good education, and we don't care what you study, as long as it's constructive. Do something that's constructive, and if you do that, we're happy." And my brother and I took this into account and did our best, because, you know, I was raised in a very poor section of Chicago. I mean, it was made up mostly of immigrants. Many of them had come from Italy, as a matter of fact. I lived in an Italian neighborhood in Chicago, and that was the prescription for raising the children and raising them out of that social condition.
Okay.
Thank you. Hello, can I ask you if you remember to the day when you found that you win the Nobel Prize? What was that feel like?
Oh, that was. It was. I have to tell you how it all came about. I was attending a meeting in Fort Worth, Texas. And in Fort Worth, the time zone is 1 hour earlier. So I got a call at 5:30 in the morning from my wife. Now, it turned out at that time, my elderly mother, who was not well, was living with us. So when you pick up a phone at 5:30 in the morning and hear your wife, you figure something terrible has happened. But she had really good judgment in saying to me, "Jerry, this is not bad news." And she proceeded to tell me, and I thought I had really not come out of sleep. I was still dreaming. That was the feeling I had. And so she told me, and then I put down the phone, and then somebody from Sweden called me to tell me. And I was just absolutely flabbergasted. And then I got one phone call after another, just continuously. I wasn't even dressed yet. I just was in my bedclothes. I just gotten out of bed. The phone call had awakened me. And so I was on the phone, and I got one call after another for I remember it was one live interview for WBBM from Chicago. That's a radio station. And there were many other calls. And then at some point, I said, I can't take this anymore. So I put down the phone. I called up the operator and asked her to take messages for me. And I got dressed. I went down to have what I thought would be a quiet breakfast. So I walk out of the elevator, and somebody greets me there, and he says, "You have a press conference in 15 minutes." So I come to the main dining room there, and there are Klieg lights set up, and lots of people sitting there from this conference already, reporters there, and I had an hour's press conference, and it was unbelievable. I got $50 million for a project by saying it was being underfunded during this press conference. So it was the one time in my life I had some influence to get some real money. And so I decided that, afterwards I had to get back home. I get on the airplane. I'm sitting there reading my magazine, and all of a sudden the flight attendant comes up with a bottle of champagne. "This is yours, in honor of your prize." And then the captain mentions it on the loudspeaker system, and everybody says, "Congratulations!" It was just unbelievable. It was an experience that it was. I still remember with great fondness. It was kind of both embarrassing and fun.
I've got here some academical question from Vladimír Kulil from Appraisal Institute of our university, and he's asking, the universe has infinite dimensions. It is also an infinity to minimum. Then the mass is made up of an infinite number of particles?
No, we don't know whether the universe is infinite or not. All we know is, we have this cosmological model of the Big Bang, and that we can talk about where the edge of the universe it was that started at the Big Bang, and where it is right now. It's about 46 million light years away from us. If you calculate the number of particles, people make estimates, the number of particles in the universe. This is what I call the observable universe. It's not, we can't observe the edge at this point, but at some point it gave out light which came here. The number of particles in the universe, I think, has been somewhere of the order of 10 to the 78th, somewhere that to the 79th. I think that's the number I remember. It's that kind of number. And in fact, if you look at the universe, the atomic matter that we're made of constitutes less than 5% of the total energy, of the universe. You see, since mass is convertible to energy, you can talk about the total energy, and the energy associated with the atomic matter that we are made of is 5% or less, and the rest is made up of things that we don't even understand. I mean, there's so-called dark energy, which is about 73%. There's something like and the rest is what they call cold dark matter, and we don't know what that is. What we do know is it's not atomic mass. So the universe is really quite strange, but we have no idea of whether the universe is infinite or not. In fact, you get into strange paradoxes with an infinite universe. And the kind of paradox is the following. Now, we exist here, right? So there's a certain probability that a system like ours, with us sitting here just now, exists. Now, that probability may be very, very tiny in the universe. You know, the fact is, how probable was it that we are all together here in this room at this time? Well, it's probably a very, very tiny probability. However, if it's an infinite universe, any number multiplied by infinity is infinity. So therefore, from our concept of infinity, this experience now is happening in an infinite number of times. And isn't that perplexing? And so, you know, when you start talking about infinities, you get into real kind of real problems. So I never talk about infinities.
Okay, thank you. Any other questions? Okay.
Just question, if I'm not wrong, Leonard Susskind and another physicist proposed the idea of holographic universe. That means that a universe is three-dimensional holograph of real two-dimensional space or universe. Did you heard about it sometimes?
Well, you know, it's an interesting idea, and so you ask yourself, what does that really mean? I mean, you see, when you start getting into multi-dimensions, you know, 4 dimensions, 5 dimensions, you know, for example, string theories in 10 dimensions, your mind, it's mind-boggling. You know, you can't picture what that's all about. I think holographic universes are probably a very interesting mathematical model, but what it means physically is certainly unclear. You know, how do you really determine it? And in order to determine it, you would have to go to higher dimensions or go into a different dimensionality to show that it's there. And so far, we haven't been able to find a dimensionality which is different from 4, namely 3 space and 1 time at this point. As much as we'd like to, and people at CERN are looking for extra dimensions, you know, since string theory is in 10 dimensions, you say, well, what does that mean? Well, 6 of the dimensions curl up in distances of 10 to the minus 32 centimeters. So, you know, that's totally unobservable to us. It's so incredibly small that it's smaller than the upper limits of a quark by 15 orders of magnitude. But, you know, there have been some theories which say, well, maybe a few of these extra dimensions go out much further, you know, but there have been models. And CERN is now looking at the LHC, they're looking for extra dimensions, and I think they have a sensitivity, any dimension which is larger than 5 times 10 to the 10 to the minus 18 centimeters. If that dimension extends out further than that, they can find it. They can find evidence for it. So that's what a holographic, you know, that has reference to actually establishing the physical meaning of a holographic universe.
Thank you.
Professor, I have a maybe a related question. So do you think that we can expect some exciting news in the second round of experiments at LHC right now? Do you think that we can expect some exciting news from the experiments that takes place in the second run of the LHC at CERN right now?
Oh, I think it's a great possibility. You know, you never can predict what's going to occur in the future, but if I had to bet, I bet there'd be some exciting things. It may take a while. You see, the thing is, we have a very successful model called the Standard Model, but we know it has defects, and one of the defects has to do with the fact that you have different scales of so-called unification, and in order to keep these scales apart, it's called the hierarchy problem. To keep the scales apart, you've got to fine-tune the theory to about 1 part in 10 to the 28th, which is very unnatural. So, for example, basically, supersymmetry has been proposed to solve that problem. And so people are looking now for supersymmetric particles. The idea is that every particle in nature has a partner of a different, so-called different statistics. So, you know, we have fermions and we have bosons. The fermions are multiples of spin 1/2, odd multiples. So you always have a half. You have 1/2, 3 halves, 5 halves, 7 halves, etc. All the others are integral spin. And so you have an integral spin, which is 0, 1, 2, 3, etc., and half integral. And the idea in supersymmetry is that every particle has a partner which has the opposite symmetry. So, for example, an electron has a spin 1/2. So you could have a selectron, which is a super electron, have spin 0. And so on and so forth. You can, so every boson, so the integral spins are called bosons, the half integral spins are called fermions. For every fermion there's a boson and vice versa. And so now they also say that obviously they have to have slightly different masses, or else we would have discovered all these partners already. And so the masses have been predicted around where the LHC can do its work. And they've been searching for these things. And you know, they may find one, who knows? But if they don't, there probably is something else that is a surrogate for this kind of mechanism to keep the scales apart. So, you know, there are all kinds of things that have the possibility of being discovered there.
I have a question, like to become successful physicist or scientist, like what would be, like what is the most important, like of the combination of, I can imagine passion, hard work, or talent. Like can you somehow order, like what's in your opinion?
I think it's a combination of all those things, and sometimes in some cases it's one exceeds the other, but you have to have hard work, persistence. Look, I've known some brilliant people who haven't really lived up to their potential for various reasons. I don't know what the reasons are. I've seen people who are less brilliant be very productive. You have the whole range of possibilities, and it's a combination of talent, hard work, passion, all these things. And I wouldn't want to try to make any kind of numerical superposition of all these things, but they're all necessary.
Okay, thank you.
I have a question. Do you think that it will ever be possible to communicate with a higher speed than the speed of light? I'm not a physicist, but I know about coupled photons. Maybe this is the way.
So communicate faster than the speed of light?
Well, because at some point maybe the people will live, for example, to another planet, and I will want to communicate with.
No, I look at it, as far as we know, that's not going to be possible. You know, there is something called a tachyon, which is a little exception that tachyons could go faster than the speed of light, even in special relativity. They have very special properties. They've been searched for and not found. Now there's quantum entanglement, and quantum entanglement can affect things faster than the speed of light, but you can't send information because in quantum entanglement, if you have an entangled system, you can be in opposite sides of the universe, and if you make a measurement on this side, it will affect what you'll measure on the other side. However, the first measurement is always random. You cannot predict what you're going to get in the first measurement. So therefore, you can't send information. So there is this principle that you cannot send information faster than the speed of light, and that seems to be valid experimentally at this point in time. Now, science can always change, so I won't say forever, but we found no exception to it, and one would have to reformulate special relativity to do it.
So maybe time for last question. So then I will ask again, Professor Friedman, do you still paint? Do you still paint?
Oh yes, I paint. Look, I'm not very good. I'm an amateur painter. You know, to be a good painter, you have to paint all the time. It's like anything else. If you want to be a good musician, you have to practice all the time. So I paint once in a while. They're not bad paintings, but you know, they're amateur paintings. So, but I enjoy it tremendously, and I enjoy other people's art tremendously. I just love art. I love music. I love all these things. I mean, I think I find a good deal of solace in the arts and humanities, and I think it's important for everybody to find such solace, I think.
So thank you for being here with us, and I wish you a pleasant stay in Ostrava.
Well, it's been very pleasant so far, and I expect it to continue to be very pleasant. Yeah. And I must say, I'm very impressed by the young people I've met here. They're really quite exceptional, and it's been a pleasure. Thank you. So I'm very honored by your applause. Thank you. Very honored. Thank you.